Here is an explanation for the answer to final exam question number 53 in Electronics Demystified, 2nd edition. If you have the printed book, please see page 428 for the question, and for a little bit of insight, go back to page 76 if you have the printed book, or if you don't, figure 3-9, which is reproduced here. What we're talking about here is a series circuit with resistance and inductance. Remember, RL circuit in series means resistance in series with inductance. We have the resistance plotted on the horizontal axis of a graph here in ohms, and the inductive reactance plotted on the vertical axis here in imaginary ohms. That's what this J operator is about, and figure 3-9 is a simple example where we have 840 ohms of resistance and J 680 ohms of inductive reactance, and that results in a certain set of points on this graph, which here is the point that we plot for J680, here's the plot for 840, and you can read the discussion that goes along with this figure. This is a little bit of a difficult question. There's some pretty highfalutin theoretical stuff going on here. But this 840 ohms of resistance plus J 680 ohms of inductive reactance is the complex impedance, and this thing that you see pointing out like that is the complex impedance vector. And the current differs from the voltage in this circuit by a certain phase angle. Now, we can't tell just by looking at this graph what that angle is, but we can calculate it with trigonometry. I'm not going to go through that right now. It looks something on the order of 40 degrees. What that means is that the current lags the voltage by this phase angle right here in a resistive inductive series circuit. The current always lags the voltage. It can lag the voltage by anything from 0 degrees, which is a pure resistance, up to 90 degrees, which is a pure inductive reactance. Now, these larger and larger and larger phase angles, as we get out, say we have a vector going off like this. I'm trying to draw a straight line. Not doing a real good job, but that vector would represent a larger ratio of inductive reactance to resistance than the vector here does. As the reactance grows to many times the resistance, these vectors get more and more and more near this inductive reactance axis, until finally, if we had a situation where the inductive reactance was thousands and thousands and thousands of times the resistance, remembering that it's imaginary, we would get the actual axis right there as the vector for the complex impedance. So this angle can increase and increase and approach 90 degrees. 90 degrees is 1/4 of a cycle. 1/4 of a cycle. So the current can lag the voltage, and that lag approaches 1/4 of a cycle as our reactance grows many, many times larger than the resistance. So the correct choice here in this question, when all is said and done, is C. Choice C, the current lags the voltage by almost a quarter of a cycle.